Okay, so let's go ahead and get started. So the first thing that we'll need to check is that we have Python installed. And so we're going to run python-v from the command line here. And you can see that I have Python 3.6 installed, and I'm currently using the Anaconda distribution. So you want to make sure that for this particular series and any video in general that I'm making on machine learning where we're using Python, that you have at least version 3.6 installed. There probably won't be too much of a difference if you at least have version 3 installed, but you'll almost certainly run into compatibility issues if you're using Python 2. And as I mentioned, and as you can see here, I am using the Anaconda distribution. And if you're not familiar with Anaconda, it's essentially a distribution of Python for scientific computing. So let's go take a look at Continuum Mechanics page for Anaconda. And if you'd prefer to download it, go ahead and download it here from continuum.io/downloads and choose your operating system. Strictly speaking, it's not necessary. It's more a matter of preference. If you're comfortable installing all of the dependencies using pip, which is sort of the default package manager, then by all means just use pip and set up a virtual environment or something. But especially if you're on Windows, I would say Anaconda makes sort of setting up a development environment in Python quite easier than it would be otherwise. And in fact, part of the reason why I'm recording this series on a Linux box is because in general I've had a much better experience working in the Python ecosystem on Linux than I have on Windows at this point in time. If you will be using Anaconda, go ahead and download the version that you would require for your computer, and it's going to do a few things for you. So it's going to provide an additional package manager called Conda, and it will provide you with essentially all of the scientific computing libraries that you might need out of the box. We won't get into too much detail about some of the really great functionality that Anaconda provides in terms of setting up environments and things like that, but I will be using it here as my Python distribution, at least for this video. Alright, so let's go ahead and head back to the command line. I'm just going to close this browser for now. Alright, so the main platform that we're going to be using in this video, and in general when we're doing things like exploratory data analysis, is Jupyter Notebook. And Jupyter Notebook is really just a fantastic tool for both writing sort of like drafts of code and taking notes, and as well as sort of sharing your notebooks with colleagues or friends. Okay, so the first thing I'm going to do is I'm going to go ahead and cd into my project directory, and then I'm just going to go ahead and make a new directory here called Spotify, and then we'll cd into that directory. So what we're going to do is just go ahead and run this command, and you'll see that the notebook is going to now spin up on localhost port 8888, and so let's go ahead, and it opened up in the other monitor, so I'm going to bring it over here, and so you can see that we have a little dashboard here. So Jupyter Notebook is a fantastic application that is used for both creating and editing notebooks running different kernels. And so we'll be running a Python kernel in Jupyter Notebook here. So we're going to go ahead and create a new Python 3 notebook. Okay, so I'm just going to go ahead and name the notebook here, and we'll just call it Spotify EDA and decision tree classifier. So we'll just call it maybe decision tree. Okay, and so you'll see we have a cell here, and what we're going to do is just go ahead and start writing Python. So I'm going to make my imports, and so we'll import pandas as PD. And so pandas, if you haven't used that before, is essentially allows us to work with our data in a sort of like tabular or dictionary style format, where we have pandas gives us access to two really powerful types: a data frame, which essentially contains a set of one or more pandas series, and it allows us to kind of reason about our data and structure it using these types to sort of think of our data in tabular format. So we'll get a better look at that here in just a few minutes, and then we're going to import Numpy as NP. And if you haven't heard of Numpy, this is sort of the de facto scientific computing package for Python. And in particular, it's going to give us a very powerful array type object here. And so it's going to allow us to do things like create data types for structures like matrices and do lots of linear algebra and things of that nature that are extremely useful for working with large amounts of numerical data. Okay, and then we're going to use scikit-learn. So from sklearn, import tree. And the decision tree classifier is what we'll be using from the scikit-learn library. And then from model selection, we'll import train test split. This is just a simple method that allows us to quite easily split out training data from test data from a larger data set. And then I'm also going to import matplotlib. Well, we'll say from matplotlib, import pyplot as plt. And so matplotlib is a just charting library for Python that makes very nice charts that you can use. And I should mention that scikit-learn is essentially a machine learning package for Python. It gives us a lot of sort of high-level methods for running things like decision trees against our data. And then I'm going to import Seaborn as SNS. And Seaborn is another visualization library, but it allows us to kind of style our matplotlib charts a little bit more nicely. And then I'm just going to do a little bit of what's called cell magic here and run with %sign matplotlib inline. And this is going to allow us to inline our plots here in an IPython notebook. In our case, we're using a Jupyter Notebook, so I'm not sure that this is strictly necessary, but anytime you see a %sign and then some sort of command that's run here, this is called cell magic. And there are a number of different things that we could use cell magic for outside of matplotlib, but we won't get into that in this particular video. And so here's the other cool thing we can do with our Jupyter Notebook. As you can see that what I did to run this cell was actually just hold Control and then hit Enter. And that's going to execute the code in the cell and then open up a new cell just below it. But in fact, we don't need to necessarily write Python in these cells. And if you select the drop-down menu here, you can see that we can also write Markdown. So if I just want to write some simple Markdown here, say like Spotify song attributes EDA, and then Control Enter, that's going to actually interpret our Markdown syntax and create a nice heading here for our notebook. So the next thing that I want to do is to actually get our data set. And the data set that I'm using for this video is actually available on Kaggle. So I'll head over there. And if you don't have a Kaggle account, go ahead and sign up for one. It is completely free. What Kaggle is essentially just a website that hosts machine learning competitions or predictive analytics competitions. And so you'll see some pretty big name companies come here and post quite large amounts of data and then host a competition for users to actually compete in order to produce some particular machine learning algorithm, and in fact provides some type of prize quite often, or swag. So anyway, that's just a quick rundown of what Kaggle is all about. So if you search for Spotify, and we're going to select Spotify song attributes here, and this will be the data set that we'll use for our video. So just go ahead and click download here. And so we'll save the file. And so what this user has done is he has collected data from his own Spotify account, and that data contains a sort of numerical value for different attributes for a particular song, and then each observation is then labeled as either 1 or 0, depending on whether this user liked or didn't like the song. So his idea was to try to develop a machine learning algorithm, in this case a classifier, that could predict whether or not he liked a particular song based on the data that Spotify provides. So you can see that there's like all of these different sort of attributes that Spotify has determined are properties of an individual song. So acousticness, danceability, the duration of the song in milliseconds, the tempo, all of these sort of kind of interesting properties that Spotify is able to extract from each of these tracks. And so that's the data that we'll be working with in order to do some exploratory data analysis, as well as build our own classifier using a simple decision tree. So if we go ahead and get that downloaded, then I'm going to head back to the command line here, and I'm just going to open up a new terminal, and we'll cd into that directory again, and I'm going to make a directory called data, And then we're just going to go ahead and move that zip file from the downloads directory into the data directory, and we'll seed into that directory, and we'll just go ahead and unzip it. Okay, so you can see that we now have this data.csv file here in the data directory. So let's head back to our Jupyter Notebook, and we can close out of Kaggle for now as well. And now we're going to go ahead and import that data. In fact, I'm just going to take some very quick notes here about what we'll be doing. We're going to import our data, then we're going to do some exploratory data analysis, or EDA, in order to visualize that data. And often we do this to sort of try to detect some structure to the data. So I'll just say and structure. Then we're going to train a classifier. In this case, we're going to be training a decision tree classifier. And then we are going to predict a target using the train classifier. Okay, so again, just Shift Enter will run that cell. And so let's create a data variable, and we're going to use Pandas read CSV method. So read underscore CSV, and then we just pass it the file path. And in fact, this is the relative file path. So we are in the project directory, and then we just created this data directory, and in that we have a data.csv file. So now, if we look at the type of what Pandas has done here, is it's created a data frame object here from this CSV. So we can now begin working with the CSV in really useful ways. So for instance, if I run data.describe, we can see some pretty interesting statistical information about the data that's in the CSV here. So we can see that for each of the columns, Pandas is going to provide us with a count of the number of records, and then the average value, some standard deviation, and a min and max, and then the percentile. So you can see we have 2017 songs here. So not a super large data set, but certainly enough to at least begin taking a look at. And yeah, kind of cool that we can kind of see some average values to get an understanding of sort of the overall structure for this data. So like the average tempo for the songs in this data set is 121.6. I presume this is beats per minute. Yeah, and a few other interesting things that might be worth taking a look at here. Just wanted you to be aware of the data.describe method. The other thing that we can do is if we run data.head, this is going to actually grab us the first 5 rows of data from the data set. So we can just kind of inspect it this way as well. You can see that we also have like the song title and artist as well. That's pretty cool. A few other methods to be aware of, I guess, are, for instance, data.info, which is going to show us that we have this set up as a data frame, of course, number of entries, and the types for each of the values that are in our feature columns as well. So from this point forward, I'm going to refer to the columns here as features, and then each row will be a particular observation. And so you can see we have this target value here. So this represents whether or not this user liked or disliked this song, and each of the different properties of that song here we'll refer to as features. So next thing I'm going to do is I'm just going to go ahead and split our data into a test set and a training set. And we want to do that because really the whole point of this is we want to take a certain amount of training data and then build up a sort of algorithm in order to predict whether or not this user likes a song. And then we want to test that trained classifier against a completely separate set of data that's of the same type. So in a sense, what we're trying to do is really to sort of like reveal a more general structure to the data such that we can make a classification based on observations that we've seen before on completely new observations. And so that's sort of the whole point and the real value of machine learning. So we can do that just by specifying a train and test variable, and then we're going to run that train test split method that makes this very easy. And as an input, we need to provide data, and then we need to provide a test size. So this is the split of the amount of data that we want to use for testing purposes. And in fact, I'm just going to use 15% here. Okay, so we'll go ahead and run that. And then in fact, we should be able to see that these data sets are of different sizes. So I'm just going to run a quick print here. And and then length test. And so this is just saying that the length of the training data here is 1,714 observations, and our test data set is 303 observations. All right, cool. So another thing that we could run here is also the shape property on our training data or on our test data. And this is going to show you the number of rows and columns. That's just another useful way to take a look at the shape of your data. Particularly if you need to kind of just sort of spot check it when you're performing certain functions in linear algebra that require your data to have a particular shape or dimensionality. Okay, so we have our data split out and we have it put into separate data frames here, as well as this overall data frame here that is in our data variable. So let's go ahead and try to visualize it a little bit. So to do that, I'm going to use matplotlib. And in fact, if you want to delete cells, the key bindings are quite similar to Vim, so if you just dd on a cell, it's going to actually remove it. Alright, so I'm going to define a fig variable here that represents our figure, and I won't get into all the details of matplotlib in this video, but we'll just go ahead and build it out and get a sense for how it works in that way. Oops, I think this is fig size. And we'll give it a title. So let's take a look at, for instance, the distribution of, let's take a look at tempo, I suppose. That might be an interesting one. And then what we'll do is we'll make a quick histogram, and then we'll see if there's a difference between the tempo in general of the songs that the user likes versus the songs that he dislikes. And yeah, maybe we can just kind of take a look at the distribution using a histogram. So I'll say song tempo like-dislike distribution. And so that's going to set the plot title. And just above this, oops, sorry, still in our cell that we're using to plot here, what I'm going to do is I'm going to create a variable for positive tempo. In other words, these will be songs that the user liked, and these will be all the tempos for those songs. And so we have this sort of query syntax provided by Pandas that we can use. And so we'll look at our data variable, and then we can run sort of a query inside of this sort of array index selector type syntax. So in fact, the way that we do that is we'll look at the target variable. Remember, that is whether or not the user liked the particular song or not. So that is this column here. And so we'll say that's 1, and from that we'll select the tempo. So we can kind of read this as saying from the data set where the target value on the data set is equal to 1, select tempo. And I'll do the same thing for the negative sentiment. In other words, if he disliked the song or didn't like the song, the target was 0, and again we'll select the tempo. And then we can just run a histogram plot type here. So on the positive tempo data frame, Pandas provides us with the ability to just say .hist for histogram, and we can pass it some params here. So we'll set the alpha to 0.7 just to make it slightly translucent. We can set the number of bins here. So I'm not sure exactly how many different tempos we'll have, but a bin size of 30 should work relatively well. And then we'll have a label of positive just so that we can see that this particular histogram refers to the songs that the user liked. And then we'll call the same hist function here on the negative sentiment data. And of course that label will be negative. Okay, and then we'll just call one more thing here, which is plt.legend, and we'll put the location in upper right. And so we can pass this legend method here a location by saying LOC is equal to, in this case, upper right. So I'll go ahead and shift enter here. And as you can see, this is pretty neat. So we can see that the positive sentiment is represented in blue, and the negative sentiment in this case is represented in green. And in fact, one thing I'm noticing here is that in general, it appears that most of the songs are within this sort of 100 to maybe 140, 150 beats per minute. And besides that, really not too much to sort of extract from what we're seeing here. Perhaps these songs, which are between, say, like 110 and 125 beats per minute, it appears as though this user significantly liked those songs more than disliked them, but it's also the most commonly occurring tempos from this data set as well. So I'll go ahead and mention this. If you'd like to customize the colors, there's a number of different ways to do it. So I'll just go ahead and hit B here, and that's going to insert a cell below. And if you want to see a list of other commands, go ahead and just hit H. And you should see a modal pop up here with a bunch of the shortcuts. So that may be useful to you. But yeah, I'm going to go ahead and create a custom color palette here for Seaborn. And I'm just going to call it red, blue. And then you can just specify an array of hex values here. So I have like a red color and a blue color. And then we'll have this palette variable. And we'll say sns.color palette. And then we can pass this the red, blue. And then with Seaborn, we can set the palette and pass it that palette. And we can also set the style, in this case to white, which will give us a white background on the plot. And then if I shift enter to run that, and then I run our plot again, we get a different color to our graph. Oops, and I just want to make a quick fix to the color here. And I'll swap these to make it a brighter blue. And so yeah, this is our blue color on the left, and then the red color on the right. Alright, so that looks a little bit better. So yeah, so you can imagine we could go through each of the features here, run a sort of histogram to kind of see the distribution of songs in which the user liked or disliked, songs that had a certain quality to them. And we could store that data just the same way that we stored our tempo data. And just to give you a sense for what this data looks like, I'm going to go ahead and Control Shift minus sign here, and that's going to separate these cells, and then I'll say B to insert a cell below here. And if I just put positive tempo out into the notebook here, you can see that it's just an indexed set of columns here, and this is a data series type provided to us by Pandas. And so it's a very simple data structure, sort of dictionary type structure, but of course incredibly useful for sort of moving this data around and working with it. So I'm going to go ahead and delete this, and then what I'm going to do is I'm going to below our positive tempo, negative tempo variables is go ahead and paste in variables that correspond to the other features, and again select out 1 or 0 so we can get the set of data for whether or not he liked or disliked the song, and do that for each feature, or most of the features anyway. So I'm pulling out danceability, duration, loudness, speechiness, valence, energy, acousticness, key, and instrumentalness. And so I'll shift enter. And then we're going to graph all of these in a single plot here using subplots with matplotlib. So we'll call this figure 2, and we'll create a new figure. Oops, that should be fig size. And so it'll be a square. And I did not mean to run that. It's just an empty figure at the moment. But yeah, so for instance, let's take a look at danceability first. And the syntax for this will be pretty straightforward, but again, I won't go into too much detail in this particular video about matplotlib. But we're going to have a third axis here, the first and second being the ones that correspond to the like and dislike on the tempo, and now we'll plot all the other feature histograms on a new plot. Oops, figure 2, and we're going to add a subplot. And the way this is going to work is I'm going to have a single figure that contains 9 subplots in a 3x3 grid. So I can specify the location of each of these plots using a add subplot method, and then passing it this sort of encoded location. So in our 3x3 grid, this is going to be location 1, which in our case will be the top left. And then what I'll do is I'll now set the label on the x-axis. Again, this is danceability. And we'll set the y label to count, because that's just going to be the number of times a song was liked or disliked within the particular danceability range provided by each bin. And we'll give it a title here as well. And so now we'll just use our positive dance value here, which you can see is our data where the target is 1, and we're selecting all the danceability values. and we'll create a histogram there. And we'll use 30 bins again because that seemed to work fairly well to visualize this data set. And then we'll have a variable AX4 in order to plot our negative histogram. Just add that to the same subplot. And we need to create the histogram for that. And I'm just going to fix this typo here. And also just clean up my white space a little bit. Alright, cool. So now we could plot this and we can take a look, but we want to do this for actually all of the other graphs as well. And in fact, this one's actually kind of interesting. I didn't put legends out on each of these graphs, but you can see that in general here we do have a little bit of a difference observed in preference for this danceability feature. So it would seem that there is a slight bias towards disliking songs with a lower danceability index and a slight preference for songs with a higher danceability index. So that's actually pretty interesting. So what you would do is we would essentially do this for each feature. So I'm going to go ahead and just paste that in here rather than type it all out. And the only thing that's going to change is, of course, the data series that you are running a histogram for and its location in the subplot. And so yeah, we're just going to plot both a negative and positive for a particular feature on the same subplot, again in our 3x3 figure at position 1, 2, 3, etc. until we get all the way to position 9. And now we're going to go ahead and run this. And so this plot is kind of interesting. This obviously has to do with the key that the song is in. And so you can see we have 12 different keys here. And according to the user's blog article about this data set, and presumably Spotify's documentation, these actually map to what would be called the standard pitch class notation, so with 0 being the key of C. So it looks like this E flat or D sharp actually has the lowest number of observations, as well as the, apparently looks like probably the highest relative distribution of dislike to like by this user for those particular songs. Besides that, we can see a little bit of structure to the data. For instance, perhaps a very slight bias towards preferring a positive valence, so valence representing what Spotify would consider how positive a song is versus how negative a song sounds musically, and perhaps a slight preference for slightly lower energy songs relative to higher energy songs, but then actually a very large number of disliked songs at the lower end of the energy spectrum, if you will. Really not too much structure to instrumentalness or acousticness. You can see that most of the songs are actually at the very extreme low end of both acousticness and instrumentalness. Same thing kind of goes for speechiness. And duration is pretty interesting here too, being that most songs here are somewhere between maybe 200,000 and 400,000 milliseconds. And then it looks like we have very small numbers of much longer songs in which it would appear that there's no real correlation to user liking or disliking those songs. Song loudness is also pretty interesting. We can see a big spike of dislike for songs at the very extreme end of loudness, so presumably this is decibel level. So that's one way to do some very high-level exploratory data analysis. Again, we haven't really gotten too much into any detail here, just kind of observing the overall structure of the data set could be quite interesting. In the next video, I'm going to show you how you can actually query the data for yourself if you use Spotify, and we'll also build our decision tree classifier. So thanks for watching, and stay tuned for that video.